Well, good afternoon or good evening, everyone. Welcome to another Magnitude Hangout here at YouTube Live. We're going to be starting in just a minute. We're just making sure all our equipment's running properly. And we're going to have an opportunity to share with you this afternoon. Pretty amazing opportunity. It's taken us about 3 years to put this together, but we'll be running experiments for you and your students aboard the International Space Station. So just hang tight and we'll be with you in just a minute. All right, everybody. Well, welcome. Good afternoon. My name is Ted Tagami. I'm CEO of a company called Magnitude. I'm here with my colleagues, Tony So, co-founder, and Kareem Sheikh, our lead engineer. And we're joined with Twyman Clements from Space Tango, who's our launch provider. He's the one who helps us get up on the International Space Station. So for some of you that have worked with us in the past, you know we've been working on this for quite some time, and we're really, really excited that 2017 is the year when we're actually getting this thing to happen. One of the big challenges on doing anything extraordinary like performing experiments aboard the National Laboratory on the International Space Station is expense. It's ridiculously expensive. And so working with Twyman and the National Lab, we've created this platform that will allow you to introduce experiments in your class for about a dollar per student per month. So it's really, really affordable. What I want to do here, just to kind of do an overview, is give you a high-level introduction to our philosophy and concept here at Magnitude, introduce our company briefly, as well as Twyman's, talk about the next generation science standards and what they mean for us as a company and for you as teachers and educators, and how they may apply for you if your state isn't currently under the next generation science standards. And then look at some sample maps, I guess. And then we're going to go right into the actual experiment itself, biology, talk a little bit about biology and how it happens here on Earth, and what happens when we move one of those forces away, gravity, and how that might affect a plant in this case. And at that point, we'll see if there's anyone that has any questions here on the YouTube stream. And then I want to turn it over to the CEO of Space Tango, Twyman, and he'll share more about the background on his company and what he's been doing to put something like this extraordinary opportunity together for us as educators for your students. And then we'll get into the actual EXOLab itself, which simulates the experiment that you'd see aboard the International Space Station. I just flipped over to the camera so you can see that. And we'll be getting into great detail here on the hardware, the software, and of course, what I like to call the wetware, or the plant and the medium in which we're growing it under. So quick housekeeping, if you've joined us through YouTube Live, you'll notice there's a comment section in the right-hand corner there. Please, throughout our session, feel free to ask your questions. We'll be checking throughout the hour here to make sure your questions are answered. If we don't have, for whatever reason, a chance to get to your questions, we will record them and get back to you on that. We believe in a digital open door, so we'll have the opportunity to reach out to you and answer any detailed questions you might have if you have a plan or an idea for an experiment of your own. With that set up, I guess what I want to make clear is our students today, whether they're in middle school or high school, or even those that are just now graduating university, they've never known anything else but the internet. And I think we know that, but we really have to let that sink in. To being some of these kids' grandfather. I mean, I'm getting up there, but the internet and the ubiquity of it and the ability for us to get information is just absolutely phenomenal. So our company, Magnitude, our goal is really to bring students right to the very edge of discovery. And everything we do, whether it's our high altitude balloons at getting up 3 times higher with a commercial airliner, or our simulated satellites that fly in high powered rockets, or in this case, experiments aboard the International Space Station. We want to bring your students and bring your class right to that very edge of discovery, because the information is here and available to us, where we can seek those answers, and we work literally alongside scientists and researchers, graduate students, as they perform their experiments. We hope they'll kick down that knowledge to us, and we have those basic tools that we can use in our classrooms based on our own pedagogies, so we can introduce those experiences that are meaningful for your students and get them excited, to get them really thinking about the world that they have at their disposal. What we really hope here at Magnitude is that we are empowering learners, that we're giving them agency, and that we're providing you tools to make your classroom even more fun and exciting than it already is. And so that's really kind of a background on Magnitude. I have a tendency to talk too much. I'm going to turn it over to Twyman. Twyman, I'd love you to introduce yourself. Tell us just a quick, brief thing about Space Tango. We'll have an opportunity to go in much greater detail. So Twyman, all you.
Yeah, thank you very much, Ted. As Ted said, my name is Twyman Clements. I'm the co-founder and CEO of Space Tango, which is a company that really enables new users to use microgravity for research and development, bioengineering, and manufacturing. And obviously the discussions we're going to have here are really about the research and development part of it. But one of our unique things is really focusing on that, using microgravity as a physics platform for creating products for return back to the planet. And so we're in our offices right here in Lexington, Kentucky, and right behind me is our ground station that we'll get talking about. I'll do a little bit more intro later in the discussion. But what you cannot see around me is essentially all the prototyping equipment that is basically all around this, my computer here, of us designing new equipment for a variety of use cases, and some of those are going to be launching on a resupply mission currently scheduled in January. May push a little bit, but that's what we're getting ready for here. So I'll turn it back to you, Ted.
Wonderful. Thank you, Twyman. So as you'll find out in just a few minutes, Twyman and his company at Space Tango are doing extraordinary work. A lot of it is really on the very advances of science. And we've been able to, through our collaboration here, it's been just about 3 years, to be able to offer this to your classroom. So pretty excited about that. Do we have any questions that have come in so far? Any questions that have come in so far?
Yeah. So,
okay.
There was one person asking about the biology of the plant, and exactly what kind of plant it was.
Okay, great.
Whether it was related to this plant.
Fantastic. So we did have a question already coming in. I want to encourage you that have just joined us, right there on the right-hand side of the video. Ask your questions, and we'll be answering them throughout. One question was on biology. They want to know specifically about the plant that's going under the experiment here. And it's Arabidopsis thaliana, A. thaliana. It's a little mustard plant. And our lead engineer, Kareem, will be sharing at greater depth of that plant in just a few minutes. So keep those questions coming, and we will get back to that question about the plant and its relation to maybe other plant species. At this point, I want to talk about the next generation science standards. For us here at Magnitude are these new standards. And I think fundamentally it shifted the thinking about how we teach, being able to focus on our core discipline practices, the disciplinary core ideas, and these cross-cutting concepts that work across all science disciplines, which are very, very important. And I do know some of us that have joined, some of you that have joined us today don't have the next generation science standards implemented or even plan to being implemented. But I think if you look at your state standards, there's a lot of parallels. There's a lot of connections here that make a lot of sense. The third pillar of those next generation science standards, beyond the disciplinary core ideas, the cross-cutting concepts, is the integration of science and engineering practice. And that's probably what gets us most excited, where you're in the classroom and you're working with your standard thinking. Maybe you're exploring biology like what we're about to do here with EXOLab. But now we're thinking about engineering practice. How might we change? How might we evolve our thinking? How might we solve a problem in a different way? And the next generation science standards tap right into that. And so that's really important. We've taken the EXOLab, which we're going to share with you in greater detail, and map this to those next generation science standards. And we think that's really, really important for the states. Like we're in California here, we're based in Berkeley. As the state rolls it out over the next couple of years, these will be mapped directly to the 6th grade curricula, 7th, 8th, all the way up through high school. So whether you're in honors biology and looking at the gravitropic effects of genomics, the genome, or whether you're now in the new integrated model, in which you're looking at physics and life science in the same year, earth science as well, that you might be looking at how the plant grows and behaves under different conditions. And so the next generation science standards helps us think about how we can bring all this knowledge, with the advent of the internet being essentially ubiquitous, to your students and give them the agency and provide a venue that's creative for you as well. At this point, I would love to talk a little bit about biology, because that was one of the questions that we did have. And so I want to introduce to you Kareem Sheikh, our lead engineer. Kareem, I think you're on camera here, so I'm going to switch over to you. And why don't we talk a little bit about the plant biology?
Absolutely, yeah. Could we pull up that first slide there?
Okay.
All right, yeah. So this plant that we're going to be studying is called Arabidopsis thaliana. It's a really interesting plant to study because, partly because it has been studied so many times before. So it's one of the most commonly used model organisms in plant biology, and that's because it has a few advantages, right? It's small in size, so it can be you can grow a lot of them, and it grows quickly, so you can grow them relatively quickly. And because it's so commonly studied, it also has a fully mapped genome. So it has only 5 chromosomes, and its whole genome has been studied and all the genes understood. And the fact that it's so well studied means that we know exactly how it grows. So its entire life cycle, you can see on this chart to the right, has been mapped, and pretty much day by day we know exactly where we should be and where we might differ from the model because of variables that are different. So in this experiment, we're going to be looking at specifically gravity and how that changes how that changes the growth of the organism between Earth and in space. So you can see here that there's a few major growth stages: germination, leaf production, the growth of the rosette, which is essentially the leaf cluster, the inflorescence, the flowering, and the silique ripening. The siliques are essentially just the fruits of this plant. So in the next slide, this is just several pictures showing how this plant grows over the first several days. So you can see the radicle emerging from the seed, and eventually the entire contents of the seed emerging from its casing. The next slide then shows the cotyledons, so the initial seed leaves. So this is actually a much higher quality than we will actually be able to observe in our experiment, both here and on the station. But it really shows you up close the biology of this plant in this early stage, which is about 6 days into its growth. The next slide actually has a video of the subsequent stages of this plant's growth. So its evolution from its initial 2 seed leaves to a plant that's probably about 5 centimeters wide or so, and it goes through the process of it growing about a dozen leaves. So that video should be playing for you right now, and I think we can let that video play through so you can see exactly how quickly it grows. This is over the course of several days, so I think this is about 2 weeks worth of growth of this plant, and it's really amazing how quickly it does grow. All right, and after that phase of growth, which we call the maturing of the rosette. So it's called the rosette because it looks like little rows of leaves. It starts its flowering process. And the flowering process is essentially when the plant grows a long, thin stalk. And this process is called bolting. And at the top of those stalks, it grows flowers. It reproduces with other plants or with other flowers to produce seeds, and these seeds form in fruits called calyx. And these calyx are, you can see perhaps in this image, the little long things that are at the end of these stalks. So that's the life cycle of the plant, and it goes through this in about 6 weeks or so, going from seed to actually producing seeds. But the phenomenon that we're really here to study is called gravitropism. Now, gravitropism is essentially the ability of a plant to grow in response to gravitational fields, right? So this video essentially just demonstrates for you what gravitropism looks like. This is a pine plant, and it's been grown straight for several weeks, and then it's been tilted on a 45-degree angle. And you can see that over the course of 24 hours, which is how long this video encompasses, this plant is already rotated to match the new gravity environment that it's in. And plants, of course, use this to have their stalks and leaves grow towards the sun, and their roots grow towards deeper water. And the mechanism for how this plant and other plants like it is on the next slide. And it's actually really interesting. And while this is something that you usually learn in college level courses, I think this is part of biology that's easily understood by middle schoolers. And it leads into a lot of other biological topics. So inside the cells that are at the tip of the roots and the shoots, there are little nodules of starch. And you can see here that there are these light gray nodules sitting at the bottom of this cell and in this top figure. The N is marks the nucleus, the A marks the amyloplast nodules. And when the plant is tilted over, like the pine plant was in the last slide, these nodules essentially settle to the new bottom. And this is how the plant knows which way is top and bottom, right? If there's an earthquake and the plant is tilted over, it can still grow upwards because it has this ability to sense, because it has these nodules that fall over. Under reduced gravity, of course, the nodules don't simply stay settled at the bottom. They can actually float. So this figure at the bottom shows nodules that are floating in almost zero gravity. So this is a rocket that was shot up by NASA, and you can see that at the top of the flight, the nodules sort of come apart from the bottom, and this is how the plant.
Any questions?
Sure, and this is how the plant essentially responds to microgravity, and this, of course, sets up the phenomena that we're trying to observe by sending this plant up in space, which is to see the different way that this plant will grow when it's under microgravity, right? So I think that gives you a quick rundown of the life stages and the phenomena that we're trying to study with this biology here. And we can, I think, go to.
Fantastic. Thank you, Kareem.
Sure.
Hey, while you were chatting, did we get any questions that came in?
No.
Keep going.
Sure.
Fantastic. Wyman, if you're there, I hope. We'll wait for Twyman to join us again from Space Tango. In the interim, as a reminder for those of you that might have joined a little late, we're answering questions throughout the video. So if you do have a question in the right-hand side there of the YouTube stream, you just go ahead and type your question and we'll get right back to it. Hopefully that answered the earlier question about the biology, about the plant itself and what's being done. Twyman, I'm going to hand it back over to you, and we'd love to hear a little bit more about the background of Space Tango, its history, some of the current experiments you guys are working on, and pretty much what you're up to. All yours.
Yeah, sure. Thank you very much. So I'm just going to talk a little bit, and then I've got some slides that I'll get into here. And you may hear the printer. There's a 3D printer going off right next to me. We're redesigning a bracket for some electrical connectors that actually will be used for the Arabidopsis experiment, the flight experiment that we'll be flying on the CRS SpaceX 10 launch, which is now in January, February. It's currently scheduled in January, if we push, we'll probably push back later in the month or into February. But what I've got behind me is our space station ground station, and really, you really can't see anything interesting right now. The non-black screen is some of our database software. The other 3 screens are actually live feeds from the space station itself. But unfortunately, we're on the shadow side of the Earth, so there's really not much to see. So I'm going to jump in here and do a slide share and let you guys talk through, and so I can talk through a little bit of our hardware. Hopefully you're seeing the TangoLab 1 slide right now. But what this shows is actually the hardware. We all know the space station, or hopefully we know that, a little bit about the space station itself, and now we're going to abstract it down from the space station down to this Arabidopsis experiment. And so this is really what it starts with, and I'll explain this a little bit later, what that hardware is. But what I touched on in my intro, Space Tango enables R&D, bioengineering, and manufacturing in microgravity. One of our big things here, one of our differentiators, is our mission is to create a significant new industry to improve the lives of people on Earth. So if we think about, there are 4 fundamental forces in nature, in the universe. We're removing one of those. And so that has, when you remove that, that has kind of, at a very basic level, it changes convective heat flows, sedimentations, a few different things like that. And then at a level above that, that changes the behaviors in a lot of different chemical processes, cell signaling, or even crystallizations. And so then if we build atop that, there are applications of those behaviors that are used to build everyday products, from drugs to computer chips. And so what we're trying to do is, what Space Tango does is builds the capability for users to capitalize on that lack of gravity, to build unique products, better products, things like that. And we'll talk a little bit about what those use cases are. But what first we got to talk about is how you do it. And so what you're looking at here is and I'm going to show a video of this installation, but that box is really what we call TangoLab 1. And that is a general research platform installed on the space station and running right now. And this photo was taken by an astronaut, Jeff Williams, back in August. It can hold 21 U of capacity, and I'll explain what that is. But we built this piece of equipment for a couple of different, specifically for a few things. And one was flexibility and reconfigurability, because we wanted something that we weren't reinventing the wheel every time. And we wanted to be able to build some of the complexities of individual experiments into individual cube labs, which again, you'll see here in just a second. And this is really the data flow of using the TangoLab 1. So remember, that facility is on the space station. So individual experiments, whether they be Arabidopsis like we're talking about today, or we have aortic muscle cells growing in one that'll be right next to Arabidopsis, to growing other types of plants. All different types of experiments are built into these small cube labs, which are about the size of a tissue box or a loaf of bread. And those are automated experiments, so there's almost no astronaut intervention when those experiments are up there. Those are attached to what we call payload cards, which are just large, exactly what they sound like, cards that are then installed inside the TangoLab 1 when those reach orbit on a variety of different rockets. So the TangoLab 1 itself stays on orbit. And then the last part of this is a customer, really we're going to start calling a customer dashboard that we're going to be rolling out and really kind of in beta for the very beta for the SpaceX 10 launch, but rolling out more and more deeply through the OA7, SpaceX 11, and other resupply launches through 2017, where customers will then be able to interact with their data and see their data coming from TangoLab 1 on orbit, and so they can interact with it just like it's that experiment was in the room next to them. Some of the use cases, and not all these use cases aren't on SpaceX 10, but we have use cases in drug design, plant biology, tissue mimetics, smooth cell culture, yeast mutations, medical device characterization, semiconductors, implantables, all different types of things, types of customers that Space Tango has been is working with in a variety of different use cases. So this is that photo showing, this is Tango Lab 1 with the door open, showing those individual cube labs. So I'm going to jump here to, give me just a second. I'm going to turn off my slide share and then do this again to show this video. And so this is a video of from August 1st of this year, showing the installation of Tango Lab 1. This is in the space station, so that's about 40, 50 pounds that Jeff Williams is throwing around there pretty easy. And you'll see here in just a second, he just kind of pushes it into the rack we're installed in. And again, like I said, that facility itself stays on orbit, whereas the individual red cubes and cards, which you'll see here in just a second as he pulls one out, those are what go to and from the space station. So we keep the facility up there, which provides power and all the networking, and just the cards themselves come back. So we'll skip it forward here in just a second. I don't want to show the whole, or bore you with the whole video, but you can see there's the cards, and then there's the cube labs themselves. And we've got a nice new revision of those cube labs that'll be flying on SpaceX 10 that can do quite a bit more. So I'm going to jump ahead here. About right here. He just turned it on, so it shows all the green lights, which is what we like to see. And then of course the last thing is we try to minimize the astronaut time, so they plug it in and then they get these green check marks that basically say everything is running okay. You'll see that here in just a second. And there we go. So that's the kind of trail of operations that the astronauts will be doing when the Arabidopsis is launched in a few months. And once that's plugged in, we'll be communicating it with this facility right behind me. And unfortunately, we're still in darkness, so I don't see any space station videos right now. But if we do see some, I might wave you down and show them around. So
that sounds like fun.
Yeah, yeah. And the last thing I'll show is this is a cube lab right here. So this is actually the structure, very similar. This is the structure that the Arabidopsis will be in. So you can see the ground version that Kareem has there, very close in size, but this will have a little flight computer and some other things in it. But this is what one of those will look like. So, and from me, that's all I've got right now.
Twyman, thank you very much.
Yeah, no problem.
For the overview. It's really exciting to be able to see that. Now, we've got a flight scheduled with you on January 21st. Subject to change. It seems like the rocket's weather and other things.
Correct.
Like that. So we are actually running, for those of you that are joining us, a closed trial right now with Space Tango with a group of 15 schools. And through those trials, we're going to be opening this up for schools for the 2017-2018 school year. So hang tight. We're giving you an early preview. We want to make sure it works well and it's an amazing experience for you. And there's a lot of things that have to line up just right. And so our first chance of being live on station will be in February. And from that knowledge, from that experience, both in class and on station, we'll be able to modify that. We're expecting probably another test during the summer, and then what you're seeing today, you can roll out for your 2017-2018 calendar year. With that, did we get any other additional QA? No? Okay, cool. If you have joined us in between, it looks like some folks have jumped on and jumped off. If you came in a little late, I encourage you to ask your questions right there in the YouTube Live. Just type them away, and we'll pick up those questions on the back half of this live presentation. So with that, I think we're pretty much on the mark. I want to hand it back over to Kareem, our lead engineer here at Magnitude, to talk actually about the device that we're running in your classroom, the EXOLab. And this is the sister of what Twyman just shared with you, that aluminum box that's about 8 inches tall, 4 inches by 4 inches. So it's called a tube. And so, Priya, I'm going to turn this over to you, and I'm going to go on mute. Why don't you share a little bit about the EXOLab hardware, some software, a little bit about integration, and of course the web and how we're actually making this work. All right, it's all you.
Okay. So EXOLab is a device purpose-built for a couple of different tasks, right? And one of the main tasks, of course, is keeping this plant alive. Now, this involves, of course, providing sufficient nutrition and a place for the plant to grow such that it grows healthily and in conditions that are amenable to students and teachers, of course, observing and figuring out what it is that we want them to figure out, right? So this involves a growth medium. So instead of soil, which usually, of course, plants are grown in, we grow it in a gel medium, right? And you can see the gel medium here in this container. Oh, wait, there we are. And perhaps, there we are. Perhaps Ted can give you a close-up of what that looks like. But essentially, it's a gel composed of four main ingredients. First is water. So that medium is 98% water. It has a gelling agent to help maintain cohesion within the gel and to provide a place for the roots to grow and spread out. It has nutrients, so things like nitrogen, phosphorus, sulfur, all the metals that a plant needs to grow are all contained within that gel. And it also has a biocide and fungicide to prevent bacterial or fungal colonization. On top of that, the device has light control, right? So you might be able to see inside this box are a series of LEDs near the top, and those are illuminating both. Those are illuminating the plant and giving the plants enough light to grow. Now, this light is precisely controlled for both intensity and timing. So this box, when it's sitting, of course, in your classroom, gets light from all sorts of sources, from the lights in your roof to outdoor indirect light. And the lights inside the device are essentially calibrated to set the correct amount, to provide the correct amount of lighting for this plant to grow consistently, so you have a high quality experiment that's being run. The other set of systems that we have are the sensor and data systems on EXOLab. Now there's several digital sensors on there that are receiving information about the environment. So these include things like temperature, humidity, carbon dioxide, and light. And those are our four main sensors. And I think Ted here is about to bring us the board for EXOLab that shows you how those sensors are laid out. Now, students will essentially become familiar with all of these sensors over the course of this experiment, because they'll be plotting them and learning data science that they'll be able to get back and work with and learn about things like data modeling, experimental design, and how to construct models for how this plant will grow over time, and also compare not only with the plant on station, but also with other plants in other classrooms using the data that they get back from these sensors. And there's also
the basic features of this.
Sure. Yeah.
I'll just point you to.
Sure, yeah. That top sensor there is a carbon dioxide sensor. Now, carbon dioxide is of course very critical for how a plant grows. Carbon dioxide is where a plant gets most of its mass, and the plant has several carbon cycles that it goes through over days and over seasonal cycles. The second sensor that we have is a temperature humidity sensor. Now, of course, both of those things are quite critical for how a plant will grow. If we go outside the range for a comfortable temperature for this plant or a comfortable humidity, you'll have adverse effects on the health of the organism. And the last sensor that we have is a light sensor. Now, the light sensor both helps the device figure out how much light is being delivered to the plant, and it also allows for science trying to figure out how different intensities of light and different timings of light affect how this plant grows. All of these sensors are built on the Raspberry Pi platform. Now, if you're not familiar with the Raspberry Pi, it's essentially a tiny computer that's built on this tiny 2-inch by 3-inch board, and that's a fully capable computer. You can plug in a keyboard, mouse, and a little SD card, and that allows you to have pretty much a functional desktop for about the cost of an Arduino, if you know what that is. But for around $35, you can have a fully powered computer, and that's what makes the heart of EXOLab tick. There's also 2 different cameras on board EXOLab. I'll bring in the actual device here so that you can observe it. There's the overview camera, which Ted is pointing to right there. Now, the overview camera provides information about the plants in the later stages of growth, right? So when the plant is so old and it's bolted and it has flowers and leeks, we want that camera to be able to observe the entire plant. So it's situated up high and pointing downwards. The other camera we have is what I call the macro camera, and that essentially gives you a close-up view of this plant during its early stages of growth, when it's really small, and it's in a state where the overview camera will essentially show a couple of green pixels, and that this will give you high-quality images of really the early and critical stages of this plant's growth during germination. And those make up the sensor and data systems that will come back to you and that you will present to your students in the lessons that we give. There's also, of course, the opportunity for direct observation. Since the device is built with 3 clear windows, you can essentially have the whole class. Yeah. Here you are. So you can see that the device is pretty much open, and what encloses it is this panel that's made up of 3 different pieces of acrylic, and this encloses the device, but still allows students to be able to observe this plant from essentially any angle. It also has markings on the side of the device to allow students to measure the height directly. And observe the height over time, and observe it going through those growth stages, observe it growing leaves and then bolting, and figuring out how fast exactly that this plant grows. Now, all of this data, except for, of course, the direct observations, are sent back automatically to the Magnitude platform through Wi-Fi. So right now in our closed trial, when we go and put this device on the desk and plug it in, it connects to the Wi-Fi, and it sends back data that is then cleaned up and managed within the Magnitude platform for easy access to teachers and students. Yeah. So I think that's an overview of the EXOLab device, the hardware, and the software that backs it up, the platform. I think Tony will be able to present.
Wonderful. Kareem, thank you for that overview. So the EXOLab is a pretty sophisticated piece of equipment that's managing all the attributes of your plant, what's happening with the carbon dioxide, what's happening with the temperature and humidity, what the current light levels readings are. The gel medium that Kareem shared with you, the phytogel, could be adjusted if that's part of your experiment. One thing we are doing in our trials is we have a control group, which obviously makes the most sense. But for those teachers that want to break those bounds a little bit and think about some different things they might want to do, they might change the chemistry of that medium, starve it or enrich it in some way, or do other things like change the light cycles, the normal light cycle to maybe something more abnormal or complete darkness or what have you. So this is a great way to study not just the gravitropic effect of the plant on station, but also what might just be a plant-to-plant experiment between classrooms, for example. So all this data, as Kareem mentioned, is coming off the EXOLab in your classroom in real time, getting up to our servers. And then Twyman at Space Tango is running these amazing experiments, space station, traveling around the planet at 17,000 miles an hour. And that data is coming down on a daily basis. And we synchronize those up. And how do we do that? Well, part of the Magnitude philosophy here is building a learning management system. And I want to introduce you to our co-founder, Tony So, who's going to share more about this platform and how we manage this data and how the students can make sense of it through different tools like notes and what have you. So Tony, I'm going to hand it over to you.
Hello. This is Tony So. I am going to share. Can you hear me now?
Yep.
Sorry, I was talking with my mic off. But anyway, I want to talk to you about how all this come together. We have a unit in the classroom. We have a plant growing on International Space Station. And what do you do in the classroom? So that we have this learning management system. This is how the teachers and the student they log on every day. Within this system, it comes with a number of lessons. Is my screen being shared? Okay. Sorry, I'm not looking at myself. So what you're seeing right now is the lessons library. And I'm going to just go ahead and click through one of them. And the teacher, all these lessons are provided for the teachers. And each lesson is mapped to NGSS standards. And this particular one is mapped to a number of 4 different standards. And also it has the lesson summaries, the lesson objective, and also different procedures for the student to go through. And also there are reference materials and the number of different keywords that they really need to learn and understand. And what I don't have here is the way the students are being quizzed as well. And I'm going to show you, well, what we are seeing right now is a dash, is the teacher area. And I'm going to show you the student area. And the way the student goes through the lessons is fully guided. And they go through one section at a time. And some of the sections that you were seeing on the teacher's area, the student doesn't get to see. For example, the NGSS mapping, the student doesn't really need to look at all that every day. And I'm just going to go through all the different sections. Now, how fast they are going through the lessons and also the quizzes that we are building, and actually we are going to be releasing that very soon. Within the lesson itself, you can integrate a few quizzes in between different sections. So this way you can test them as they are going through the lessons. And in the background, we are monitoring how long it takes for one student or one group of students going through all the different sections. And the teacher will have a dashboard to really monitor live how the students are progressing. And this I want to draw your attention to this one really cool feature of ours is taking notes. And the students are encouraged to take notes, especially every single day. They should really spend about 10, well, maybe 5 minutes talking about what they have observed, what the plan has if the plant has grown or dying or whatever that is, they should take notes over here. And their notes are being recorded. So every day you can look at what they have recorded as their own notes. For example, it could be, oh, the leaf is turning green or turning brown, and or the plant has grown from 2 inches to 8 inches in 1 week, or whatever that is. And they can easily access this note-taking very easily on this side, just by clicking a button right here. And at this moment, we do not have the teacher dashboard built yet, but it is coming in a week or two. I'm not able to demonstrate that today, but it is coming. And what that does is that the dashboard for the teachers, they can see the live progress, and it gives the teacher a live reporting of how the students are doing every single day or throughout that whole class or lessons. And also they get to see the quizzes, how they are doing through the different lessons they have. And another thing I want to show you is the EXOLab page. Now, this is where they get to compare the data and the visuals from both the classroom and also the data coming off from the International Space Station, side by side. And if you see here, it has all the temperature, all the data captured from the classroom, and also all the data captured from the International Space Station. And by clicking of this one button, you are able to see the charts of all the data that is captured, and you can click to see just to see the temperature, or all of them overlay on top of each other. And also you can adjust the date range. For example, you really want to you really want to have the student to think about what happened from week 2 in the classroom versus the data from week 2 from the International Space Station. And this is an extremely good, great tool for them to really see the data and make their own comparison and reporting. Did I miss anything? Yeah? Okay.
Fantastic. Tony, thank you so much for that overview. So there's some interesting things that you see here. What's important is these experiences here on the station, in your classroom with the EXOLab. We're really looking to build this learning management system. So as we roll this out in our trials here in spring, these will be ready by the end of this school year. They will definitely be in place for you for the fall along with EXOLab. Assessments are really, really important. And one thing that Tony brought up at the very end of that, I'm enamored with, and that's the power and the knowledge of understanding how you can interpret data. Data science is a skill, statistics, essentially, that every modern person in the 21st century here is going to need to know to some degree, whether they're in a cube somewhere, whether they're an entrepreneur, whether they're tuning your automobile. They're going to want to read information and understand what that means. If they're more experimental, they may take that and judge that data to make some new decisions. And if they're looking at weblogs or what have you, they're going to be using that data for different purposes. So data science is a real powerful component to all the things we do, EXOLab being one of them. Really what we did here at Magnitude is we started with the hardware really kind of at the edge of the wedge, if you will, with the integration of science and engineering practice. We have some students that are on the path right now to actually build and launch their own satellite. And we haven't started working yet, I'd love to chat with you guys about having those kind of capabilities. What we want to be able to do with EXOLab is be able to introduce something that is fairly easy to set up, really easy to get, deeply engaging, and introduces engineering in a way that addresses your classroom. It doesn't overtake your curriculum. It supplements, supports, and reinforces your lesson. So we like to kind of flip it around. When most people talk about engineering, they want to lead with the engineering first. And you've got so many other things you have to do. It's so much easier if you can start with the main ideas. You know, what's the phenomenon you want to understand with your students, and then back into the engineering. So that's what we're doing with EXOLab. And at this point, I think we're going to wrap up, but there might be some additional questions. But what I want to make sure everyone knows is we're offering a special right now here at the end of the year for you to pre-order an EXOLab for your class anywhere in the United States. And actually, I think we have some visitors that joined us from overseas. I think we're going to be including them in fall as well. And that provides a $300 discount to EXOLab for signing up early. And you don't need to worry about payment until June 1st. And if you're talking about your new fiscal year, it might be July if you want to do it then. But we'll be shipping over the summer. And just like we're doing this Hangout right here, we're going to be providing online coursework for you as teachers, or if you're a principal that's joining us, for your teachers that come join us. And we can do professional development right here with modern technology, where we can walk through lessons, we can answer questions, and we can provide support in hopefully a very scalable way. So we're really excited to be able to join with Space Tango after 3 years worth of work, and the National Laboratory on the International Space Station to provide this for you. So as I mentioned early when we started this, typically to run an experiment on station at just half the height of the current experiment we're running right now, a 1 unit, it's about $50,000, anywhere from $30,000 to $50,000. So an experiment like this might be anywhere from $60,000 to $100,000. And now what we'll be able to do is, by introducing a single experiment that has broad applications, hopefully interdisciplinary applications, we can now spread that cost across many schools and reduce that down to right now $1,200 with your $300 savings. I think we're providing a code here after. It might actually be right on the YouTube site. If you don't have that code, we'll make sure you get it. And that's good through the end of this year. So do sign up. Again, payment isn't required until mid-2017. That's when we'll be shipping, and that's when we'll be setting up our coursework for online study and engagement with you for your professional development. At this point, Kareem, did we get some additional questions that we might want to answer on the video?
Sure, yeah. Okay. Erin Barron asked, she asked a couple of questions. One of them was, how did the kids get involved in this opportunity? And secondly, are the kids involved in the design of the experiments that are conducted aboard the International Space Station, or are they observing an established experiment?
Oh, great. So Erin, I don't know what school you're hailing from, but you had two questions. How do students get involved with it, and can they actually manage, create, set up their own experiment? So what we wanted to do is introduce these amazing experiences at a very affordable price. If you want to do a custom experiment wholly on your own from the very beginning, seed of an idea, create a hypothesis, and go through that whole setup, expect 6 months maybe at a minimum, up to maybe a year or more planning, getting some engineering and what have you, at a cost of $30,000 to $50,000. With this, what we're trying to do is set up a base experiment in which it provides branching, where you can then explore subsets of the main idea. So there is flexibility, there is engagement of your students, and we hope when they're offered this as an opportunity, they can see, here's the basic things we're trying to do. Let's imagine if you could change things like the phytogel, the little gel medium? Can we take that phytogel and make it drier, right? Can we make it wetter? Can we add sugars? What happens if we don't have antibacterial agents in it? Is this going to get overgrown with fungus? What if we tried it a different species? Maybe we want to try the dwarf variant of Arabidopsis thaliana. Those are some things you might want to explore. That's just on the wet side. On the hardware side, you might want to adjust lighting levels and what have you. So what we're trying to do is think about affordability and provide that flexibility. If you're interested in doing those extraordinary experiments, there are schools that do it. It's just really, really expensive. We're more than happy to work with you and coordinate with Space Tango to do something like that. But do plan to do a lot of bake sales and get a lot of support on the engineering side. One thing that we're really interested in is being able to reach all the students and work with the national lab. There are 50 million students just in the US alone, K through 12. Our goal over the next 10 years is every single student has an experience aboard the space station. And there's some interesting things, hopefully we'll be able to announce in early spring about how we can make that accessible to everybody. But this EXOLab right here is designed right now for plant biology, but we've got some other ideas that we're already working on. Let's look at bugs. So entomology. What happens to an ant colony in microgravity? Or maybe it's a winged insect. How might it behave? Providing that NASA gives us the clearance to fly something like that, we'll get it up there and we'll open it up to all your classes. I'm gonna guess we might run a trial during the summer, but those probably won't start until 2018. Or maybe it's material science. We might actually go macro and think about, or micro rather, with a macro lens, and think about crystallography and how crystals might grow. And there's some interesting research there on the material science front, and you'll see a lot of research if you look at the white papers and what some graduate students are doing. That's very fascinating to us, and we'd love those kind of explorations to be available to you as well. So this EXOLab, as it's designed today, is a growth chamber for plant biology, but we see it easily expanding at really very low cost into other areas of exploration as well. So I hope that answered your question. Do we have additional questions?
There were other questions in that same vein. So,
okay.
So do the students control the experiment on board?
Great. So there were some other questions along a similar vein. Can you control the experiment aboard the ISS? So originally when we thought about this and we kind of scoped it, we thought, wow, wouldn't that be fascinating to have the students be able to change the light levels and what have you? But once you start thinking about it, if I've got, let's say we've got 50 schools up there or 300 schools, I've just ruined everybody else's experiment if they're waiting for something to be very, very consistent. So what we're really trying to do is set a benchmark, and here's the set experiment. And the variables of that can be done perhaps in the classroom to compare, but really we're going to want to set that thing up as standard. There's probably a lot of different ideas that you guys might be thinking of that we haven't covered yet, that you're coming across. We're a very firm believer of engaging with you as educators and thinking about what might be possible. We have some ideas, but if you've got something really, really exciting and that really interests you and you want to explore what might be possible, if it's a really awesome idea, let's build it for everybody. So let's go ahead and set that thing and put it in motion. Now, we can't guarantee that we'll do that with everybody, but we're always open to ideas, and we'd love to see what you guys can come up with. So for now, I think we're kind of wrapping up our hour. What I'd like to do is, unless there's some additional questions, remind you that there is a $300 discount for the $1,500 EXOLab. So instead of spending $30,000 or $50,000 for an experiment for one class, we're now creating this EXOLab for a much more affordable price. And that actually will come with 3 of these gel packets. So you can run 3 experiments over the course of your year. So it's not just one experiment. So perhaps you did want to run with A. thaliana, and then maybe you want to try a dwarf variant or do something else. Maybe you want to try to change the medium, or maybe you wanted to change the light levels or some other function of the EXOLab itself. So 3 packet comes with the networked EXOLab and the platform that Tony described to you in all its glory, this learning management system in which you can track and assess your students both formatively in these quizzes or checking for understanding, if you will. A little less of a fear word. I think some students get afraid of that word quiz. So we can check for understanding, and then you can get a summative assessment as well, where at the end of the lesson, they have a pretty good understanding of what's happening. I'm going to imagine there's probably some additional questions that you guys come up with. We have a digital open door. Please reach out. Let us know what your ideas might be or what questions you have. But please come join us. There's going to be a lot of fun in low Earth orbit in 2017, and I hope you're a part of it. Thanks so much for joining us here at Magnitude and joining Twyman Clements and the team over at Space Tango, and we'd love to see you in orbit with us next year. Take care. We'll talk to you real soon.